Hi folks, and welcome back to Physics with Captain Rod. I'm making this to be kind of a conceptual video about why velocity graphs are so useful for studying the motion of an object. So again, when you're studying kinematics or the study of motion, you're typically interested in the relationship between three things: the position of an object, which I'm going to represent here with an x here, meaning that I'm going to define a coordinate system here in a minute, and x will represent the position of the object. The velocity of an object, now that tells us how fast the position is changing and whether it's increasing or decreasing, right? And the acceleration of the object, that tells us how fast the velocity is changing, right? So this one's telling us where it's at, this one's telling us how this is changing, this one's telling us how this is changing. And for this video here, I'm going to be focusing mainly on these two. Now, when you're studying the motion of an object, the first thing you typically do is you define some sort of set of coordinates here. So I'm just going to come back here somewhere, and I'm going to put a coordinate system right here, x. Now, whether or not you put the y-axis on here does not matter. I'm going to go ahead and put this here just so that this looks like the standard coordinate system that you have seen, maybe from algebra class. I tried to orient it in such a way that the x coordinate of the car, and we're just going to measure that to like the middle of the car here, is changing, but the y coordinate is not. And the y coordinate is basically 0. Now I said basically because, I don't know if I have this lined up exactly with that dot there. We'll do that. So now I've got that coordinate system aligned so that the x coordinate is changing but not the y. The y is 0 the entire time. Let me kind of redraw this here. Alright, so this now is x, which tells me the position of the car. Now I'm going to go through this first numerically, assuming that car is moving at 5 meters per second constant. Now, you notice, I didn't put the coordinate system like to the right or anywhere over here. I chose a spot here. It doesn't really matter where you put these. A logical place to put that coordinate system would have been maybe here. At that point, we would have set at t equals 0, x was 0. And that would be a perfectly logical, acceptable way to work this problem. I'm going to go ahead and just leave it over here, just to make the video a little bit more on the generic side, and say that at t equals 0, x is 20 meters. Just making up something off the top of my head. Now, when you study motion, typically you want to start with your velocity graph, because once you have that thing figured out and you have its details figured out, typically it's a one-step process to your position information or your acceleration information. Now, you can't always start with a velocity graph. Sometimes you have to start with a position graph, sometimes you have to start with the acceleration graph, but normally this is the one for most cases I look at that I try to get students to draw first or think about first, because the velocity graph tells you what the system is doing. So at t equals 0, this car is moving at 5 meters per second. So I'm going to put a point on the graph here, 5 meters per second. Now, this is not changing, so a second later, the car is still moving at 5 meters per second. A second later, the car is still moving at 5 meters per second. Now, you notice I've already done the motion diagram for the car. The delta x's are not changing. This is the motion diagram for a car that's moving at a constant velocity. Now, functionally here, I'm going to start putting position graphs in now. At t equals 0, our car was at x equals 20. So I might come over here and I'm just going to put the 20 right there, 20 meters. Now, a second later, this car is going to have moved 5 more meters. So the next dot is going to be 5 meters higher at 25. I'm just going to put that right here, slightly higher. Then the next dot, 5 meters higher, and this is going to increase like this. Now, the relationship between these graphs, very, very important. First of all, the slope of this line, right, remember velocity is delta x over delta t. So velocity is the slope of a position against time graph. So the slope of this line I'm mapping out is going to be the velocity of the car, the 5 meter per second. So that's how they're related this way, by slope. But they're also related by this way through area. On this graph right here, this area right here is 5 times 2 is 10 meters. And what that gives me is, right, not x, it gives me the delta x. The car started at 20, increased by 10. The x coordinate for this point here is 30 meters. Now I can repeat this process for any time we wanted to. I could go to 3 seconds, 4 seconds, 5 seconds, calculate a delta x for any of those times, add it to my beginning time, and I would have my new time, or my new position. I'm sorry, add it to my initial position, and we'd have our final position. Now, you'll notice, think qualitatively what we're doing. We are saying x at any given time is equal to, numerically, where we started, 20 meters, plus some change in x, and here's the very important part, and we are getting that change from the area of this rectangle. Now, we can actually use this fact to derive a function over here. So imagine I take my graph a little further, except rather than nailing down any time here, or a number, let's just call it t, where that t can be any time. Then our delta x, which is given by this area, do this in red, would equal, in this example, 5 times t. 5 times t. So I could actually write this function. 20 meters. Let me just leave the units out. We'll put NCU for note consistent units, plus 5t. And you notice what we have now is a function. We've used the area under this velocity graph to find the function for that curve. And this equation is good anywhere. And I could generalize this even a tad bit further and say, well, x is a function of t we're going to get from, now at first I called this 20 meters, but if I want to write this in a little more generic sense, let's call this x sub 0. X sub 0 being the x coordinate at t equals 0, plus this area here. Let me just put, I'll just put area here, where this thing typically will be some function of t. In this example, what we have is x sub o plus the 5 is our initial velocity, and then times t. And this is one of what are called the equations of motion. So, backing up, for constant acceleration. Now, in this particular example, we had a constant velocity, which yielded a linear position function. So, I'm going to make other videos that look at a little bit more complicated examples, but it turns out when velocity is constant, position ends up being linear. If your velocity were linear, your position function ends up being quadratic. When your velocity function is quadratic, your position function ends up being third power. And this relationship will always hold. And again, I'll make more videos about how these equations are derived. This was just meant to be a very simple conceptual video here, demonstrating why the relationship between our position graph and our velocity graph, when we are going this way, we can use this concept of area to calculate positions or to find functions for our position graphs. So again, just a conceptual video. I'll save the more complicated examples for other videos. I hope that this helps. Have a great day.